Okay, so I'm ready to get started, and it's about to get started too. So I hope you too. Today there will be a total of 4 deafening class quizzes. So I'm going to read you one of the questions that was in the last week. That if we're going to learn that, that will be the very important in terms of the written exam. In order to make that happen, we need to look at a few things related to eigenvalue analysis, and that's something that helps to understand the model reduction. And then I added one more week here, so that's going to be the next Monday. So that's going to be preparation for the exam. And that's I promise that I will give you a list of questions, and that's what I do. So this was the deal that we made. So you come here, one additional week, and as a, kind of like the what you can get from your hard work and effort is that I will give you a list of questions. So there will be all the questions that I will ask in a written exam and few others. Then you just need to cover, say, few topics, and some of them will appear in a written exam, some of them will not. Sounds good? Okay, so that's the way to go then. Shortly summary what we discussed about last week. So last week we discussed about as a result of the polynomial expansion, the shape function matrix is like the nature of the inherent nature, the soul of finite element method. And what is that they're telling you? They're telling what are the expected deformation within the element. So if you have like extremes of the element, so not the entire structure, but the single element, and one single element starts from the nodal location and it ends from the nodal location. How the particles between these behaves. So this is absolute value when you multiply the shape functions by nodal degrees of freedom. So it's a kind of the same concept that we're using in a model reduction, because in model reduction we have assumed deformations. But how much one deformation will contribute, that was mentioned by this modal coordinates, the amplification. Here the concept is more or less same. So we have assumed deformation, which is kind of expressed by using the shape functions, and how much the one shape function will contribute, that is expressed by vector of nodal coordinates. So that's how it goes. And here's a picture of few examples how the shape functions look like. And something that is important to recognize from this picture is that the shape functions are orthogonal. Orthogonal meaning that the one shape function will only affect the 1 degrees of freedom, nothing else, just the 1 degrees of freedom. Here's an example. So if you have a beam element, here in a location x equal to 0, that's where the first node is located. X equal to 1, that's where the second node is assumed to be located. Now if you introduce the unit displacement along the y direction, this is how the deformation is assumed to take place. This shape is coming from the polynomial. All right? But if you look at this carefully, this shape is not introducing the displacement to any other nodal coordinates except the one that is imposed to. So here the rotation is equal to 0. Displacement here is equal to 0. Rotation 2 is equal to 0. So that's where the orthogonality property is coming from. Okay? But you understand what the shape functions are. What is the inherent nature of the shape functions? Okay, that tells you how is different ways that the element can perform. Element can deform. Okay? So let's get started. Today's in-class quizzes. So my first in-class quiz is this: physical interpretation of shape functions. And let me put it on. So hold on a second. I need to log into Socrative. Uh, and then once I'm logged in, then I will read this again. Gonna now launch this one. Okay, so let's take a look at this again. So I'm asking, uh, what is a physical interpretation of shape functions? The first option is that it shows the way that an element can deform. Then it shows the strain distribution within the element, defines the strain displacement relationship, no clear interpretation. So those are the options. Now, out of these four options, two kind of make sense. But then you need to think about, like, out of these two, what makes sense, the one is not possible with only looking the shape functions. It needs some additional information. And for that reason, there's only one correct answer. But which one? Uh, Let me take a look. Like, how is we doing in terms of the answers? So we have 16 students, 17 students. Please don't log out because there is going to be another, well, more questions coming soon. So I want to share this with you. Um, 5 are still thinking, and then 4 are still thinking. Are you guys all done now? Not yet. Gonna wait a few more. Okay, 2 more, and then we're good to go. 2 more. Okay. How is gonna be the success rate in this question? 76. Oh, no, no, it's gonna be much higher than that. Oh, 19 out of 19. So it's a moment of truth. Where is it now? Here. 20 out of 20. Okay, 100%. Close, very close. So it's so let me see. 95, 95. If you round it up, what's that? 100%. So very good. So the other one that kind of makes sense. It is true that this makes sense. This so the strain distribution within the element. It kind of do that, but strain is something that you first need to know the displacement. And in order to know the displacement, you have to multiply the shape function by nodal degrees of freedom. Correct. And then you have the displacement. And then from the displacement, you can compute the strain. But directly using the shape functions, you cannot know that. So the strain distribution is kind of in that neighborhood, but it's not correct because it needs additional information. And additional information is nodal degrees of freedom. All right. So let's continue then. Where is my pointer here? Okay. And today I'm going to go really slow because there are a few matters that I really would like you to understand. We're going to go then back and forth until you're completely bored about the topic, but that's kind of the intention of today's lecture. Okay, a few more matters that we discussed last week. So we discussed last week that using this concept of shape functions, we can actually create the description of inertia, which is a mass multiplied by acceleration, and elastic forces, which is a stiffness multiplied by displacement. Then that's equal than external applied forces. So that's the equation of motion in finite element method. And really what we are interested in, so why we're doing this, is that we wanted to express this displacement because this displacement tells me how is a deformation of a deformable body with respect to body reference coordinate system. That's the reason that I'm doing it. And because this is expressed in a dynamic way, I have here the displacement in such a way that it is acceleration. So I need to integrate the velocity from the acceleration, and from velocity I can finally get the position. But cutting the corners this is how the equation look like. And this is where we have the problem, because typically when you look at the typical finite element model, the dimensions are very high. They could be 100,000 degrees of freedom, even more than that. So that's what makes it difficult to solve this equation as it is. So it's simply that the dimensions are too large. There's too many unknowns to solve, because the vector of unknowns here associated to deformation could consist of 100,000 unknowns. So that's too much. And that's where we have to take the model reduction. And that's exactly what we're going to use. Now, idea of the model reduction is that, if you conduct it, let me explain the full story first. So now, if you have the finite element model, let's just look at that. We have the finite element model that is a beam made by using the beam elements like this. So this one consists of 1, 2, 3, 4 elements. So 4 elements. Now, the number of degrees of freedom in the entire structure is defined by the number of nodes and the degrees of freedom at each one of the nodal locations. So let's think about that this is the most simplest beam element you can think of. So there are 2 degrees of freedom at each nodal location. So it's going to make like 2, 4, 6, 8, 10 degrees of freedom. 10 degrees of freedom in this structure. Now, if I conduct the eigenvalue analysis for this example structure, I will get 10 eigenvalues, because this system is n-dimensional and the n here is equal to 10. So I will get 10 eigenvalues. Okay? What are the eigenvalues? Those are the natural frequencies associated to this particular structure here. So the first eigenvalue would be like, let's say the numerical value could be 20 hertz, then 50 hertz, so on and so on. I can compute that until I will get ID 10, and the ID 10, they could be numerical value, could be like 200 and 2,500 hertz. Okay, those are the eigenvalues. So that's the kind of the nature of the structure. I can also compute the eigenvectors associated to each one of these numbers. And eigenvectors, they will show what is the deformation mode or vibration mode associated with each one of these frequencies. So the first one will be perhaps the bending mode like this. Second one will be, again, bending mode like this. And then more and more complicated modes until you will reach this value here. Now, if I express each one of these modes by using a matrix, let's call the matrix, that's the way that the first mode, it is the one that is shown here. This is expressed here as a vector that shows the way that the system can deform, just the way it can deform. It shows the relative displacement, how is the displacement associated with this vibration mode. All right. I could do the same for the second one. So it's the second one is again showing the relative way that the structure can deform. And then I will go all the way here to ID 10. Now if I multiply this by vector that is unknown, now this time the unknowns are the amplifications associated to each one of the eigenvalues, which are then P1, the model coordinate P1, P2, all the way to P10. This is exactly the same that my original equation of motion. I make no compromises regarding the accuracy. I'm just moving the one space, which is a nodal degrees of freedom, to modal degrees of freedom. But I make no compromises regarding the accuracy. The solution is equally accurate no matter which is the way that I use. Are you following me? So I'm replacing my nodal degrees of freedom, as it is shown here, by modal degrees of freedom. And what is between here is equal. So it's exactly the same. So no compromises when it comes to accuracy whatsoever. So this one here is this matrix that consists of these deformations that are coming from the eigenvalue. And I have a total of 10 because I have 10 degrees of freedom in my original structure. Okay, you're following me. All right, so we're good. Do you mind if I repeat this a couple more times today? Because this is what I'm going to ask in written exam. Or you just, you don't want to hear this story any longer. Should we do a little bit of thinking? Let's think about this concept a little while. So again, I have my structure here that consists of 10 nodal degrees of freedom. Nodal degrees of freedom. My vector of unknowns will be, the u displacement this direction in my first node. Let's call this as a node number 1. So u this direction. Theta associated to same nodal location. Then the u2, which is again displacement this direction, and then the angle to and this and until I reach theta 5 because I have 5 nodal locations. Clear? Okay, these are telling me how these individual points that are called nodal location, how they will actually behave. And I'm going to replace this expression by assumed deformations, which is how the entire structure will behave and how is a relative displacement in a different kind of deformation modes. And these deformation modes I will get from the eigenvalue analysis. An eigenvalue analysis tells me what is a natural frequency, like these numbers, and associated to eigenvector, which tells me how is a vibration at that particular value. All right. So I will get 10 different deformation modes. And I could create this matrix by using these 10 different modes. And now if I multiply these modes by unknowns, that is a modal coordinates, there is a total of 10 modal coordinates. I will get exactly the same response by using nodal degrees of freedom. Okay, so the question is, why? Can you explain it? Why? Like just to show that you're pretty good in mathematics, you're moving from nodal degrees of freedom to modal degrees of freedom. Any other reason? So you guys, so Team Czech Republic knows the answer, but unwilling to release it.
Usually it's because you convert some multiple degrees of freedom solution to many 1 degree of freedom.
Correct. That makes sense because this is that's a, by the way, beautiful answer. It's a beautiful answer because there is a certain kind of special feature that comes along with this matrix here. The special feature, this is a quite mathematical, but the special feature is that these eigenvalues, they're all orthogonal. So they are not related to each other. So they are all independent. They are not, the product of others, but they are only, the unique solutions. This So this is how the original equation of motion was. Oh, oh now it looked very bad because my pants got wet. Okay, so here, what will happen as a result of that is that I have this transpose multiplied by mass multiplied by its original form p dot dot. Then this one here, which is a stiffness, and here is a transpose p equal than like this. Now, as you say, now the beauty of this method is that, this one here, which is associated to one or this one that is associated to modal accelerations, this is actually diagonal representation of inertia. So it's meaning that modal coordinates are not coupled, but they are, each one of them are independent. This one here is a diagonal representation as well. So it's meaning that there's no coupling like in the original finite segment method. So that is a reason to do that. There's an reduction is about. So that is a modal reduction technique. So I'm eliminating the coupling and then I'm reducing the size. And that's what makes it possible to solve this, all this in convention or together with the multi-body system dynamics. Okay, how it sounds so far? You still awake? Okay, so let's take a look at this. So I'm going to repeat it again. I'm going to repeat it this couple more times. But this is what you get. This is the summary from the previous lecture. So this is what happens when you do the eigenvalue analysis. So you will get this equal number of eigenvalues and the number of degrees of freedom. And then you will get equal number of eigenvectors and the number of degrees of freedom. Now, if I have originally this 100,000 degrees of freedom, it's easy to imagine that not all of them are important. Maybe just a handful of these values are important and less are insignificant. And if they're insignificant, I can easily ignore them without sacrificing the accuracy too much. Okay, now this is what was happened last week. So I'm simply gonna just show you again shortly. This was our structure that shows about this spring uh, element, the spring structure that consists of 1, 2, 3, 4 nodal degrees of freedom. In this case, each one of the nodal degrees of freedom consists of 1 degree of freedom only. One nodal location consists of 1 degree of freedom. So this is how the stiffness matrix for this structure look like. This is a mass matrix for the same structure. And using this eigenvalue principle, I can compute the eigenvalues. And there's going to be a total of 4 eigenvalues because of the 4 degrees of freedom. Each one of the eigenvalues are associated to eigenvectors. And eigenvectors, you can get it from the same equation by substituting eigenvalue at one at the